evaluation and stop the class during that time, as this paper says. It is time in the semester where we ask it, etc., etc. Maybe I'll drink water in the meantime. I will come back there doing something. I'll come back in 2 minutes. Drink water.
If we're doing things with summations,
Yes.
using the mode, and I guess we're working off similar property that's in Fourier transform. Are we going to use the Fourier series to do an opening summation?
Yeah, later on in the course we will do in one particular case Fourier series summation. And sometimes this Fourier series can be summed up in a closed form.
I can't remember if we discussed it when we had the discontinuity. Is that why we were using the average between the beginning and end? Or like when you have the limit from the left and limit from the right, on one side it's 0, on the other side it's a value?
Okay, the question is, I must repeat the question. So when we do Fourier series, why do we have to average sometimes values when discontinuity is involved? So that is actually a definition of a function in a point. Function is defined as half sum of the limit on the left and limit on the right. That is how the theory is being built. Otherwise, we as engineers can imagine that there should not be any discontinuity. Discontinuity occurs when there is concentrated load, point load. Then, for example, shearing force is going from minus P over 2 to plus P over 2. So the question is, what is the value at that point? Maybe I can depict this. It's easier to depict and talk. Oh, actually, I have already 7. So there is this load, P. Then shearing force looks like this. So that is free body diagram. Okay, so that is P over 2, and that is minus P over 2. Question, what is the value of Vy at L over 2? Okay, here. So that is say L over 2, L over 2. Answer, it is P over 2 minus P over 2, 1/2, which equals 0. So here, actually, this is 0. Now, we actually let us justify this. I mean, this looks like a formality. Looks like mathematical formality. But that is not so. Actually, this is an idealization of such a case. Okay? Load is distributed. So that is, say, epsilon. And therefore, this load is P divided by epsilon. So actually, it is a distributed load. So then Vy is like this. So this is still P over 2. Excuse me. So, okay, I will give it. So that is P over 2 until here. And here is also P over 2. But here it goes like this. Okay? Because this is a distributed load. One can show that in the middle that is 0. So when this epsilon goes to 0, we get actually such a function. Look, please. P over 2, then here is 0, and then that is how we should understand. We do not say it in strengths of materials, but that is how we should teach. We should teach that this is straight line and straight line here, and here is 0. Because this load, this is an idealization. Such a thing does not exist in nature. Okay? This is an idealization of this case. Distributed load on a very small distance. Say it again. Idealized means simplified. No. The notion, that is, notion of concentrated force. Force that acts in a point, in a single point, is a simplification or idealization. Idealization means that we did not want to talk about loads that are distributed load on a very small interval, etc. But instead of that, we said, okay, forget this. We will talk about load that acts in the point. Does it answer your question? Okay. Any other questions or discussions? Okay. If not, then we will discuss one more problem. And that is topic 22. And that will be simply supported column excited by a harmonic load in the middle. The most interesting thing is that suddenly this topic of mechanical vibrations embraces in itself everything that we studied in mechanics, everything that we studied in statics. Then suddenly, unbelievably big amount of topics of mathematics like Fourier series, infinite series of expansions, etc. That is why Fourier series were developed in the first place. Fourier himself developed Fourier series to deal with these beam vibration problems and other things. Okay, and of course also heat transfer, etc. So we have this problem. Look, I will put it in the middle. Why I will put it in the middle, you will see later. P0 sine omega t. P0 is amplitude. Omega 0 is given driving frequency. Okay? Or just excitation frequency. Okay? So then again we have to write down EI d4w dx in force power plus rho a d2w dt square. Now this is a concentrated load here. Here should be qy of x, distributed load. So therefore we will write it down. This is a distributed load. So therefore this is minus P0 sine omega t, and that is a delta function in x minus L over 2. I'll explain you what is delta function. This is called Dirac's delta function. Dirac's delta function. So Dirac, physicist, Nobel Prize winner. Okay, what is this distributed load? I wrote this in such a manner, so delta function is like this. Delta function x minus a dx is something that is like infinity. I'll write down delta function x minus a is 0 if x is not a, and infinity when x goes to a. But it's not just an infinity. Integral from minus infinity to plus infinity, delta function equals 1. If you studied machine design, then it is, say, x minus a minus 1. Machine design. Or you studied maybe strengths of materials. In there, maybe you had these singularity functions. Okay, that is no connection with statistical distribution, except that in statistics or in theory of probability, such function could occur when we have discrete events. Their probability density contains delta functions. But with statistics, only the distribution functions. So what it says actually is as follows. This allows me, delta functions allow me to represent the concentrated load as a distributed load. Thank you so much. So you took this. Okay, thank you. So delta function allows me to actually represent concentrated load as a distributed load. I actually say that, you see, it is a distributed load, but everywhere it is 0. Only when x equals L over 2, it's not 0. Then its density is very big. That is what I had before also, if you remember. Pay attention. When epsilon goes to 0, this load goes to infinity. But, interestingly, the area, what is an area? Total load is value times the width. So P over epsilon times epsilon equals P. So it was the same concept. It is the same concept, distributed load. So I introduced it as distributed in a very small area. If it is in a very small area, the value is very big. So for example, if you want to, just an example. If I have a string, and here there are some concentrated masses. So that is value A1. Here is A2. Here is, say, A10. Then I can say the density equals density of this equals density of the string plus summation. So that is M1, M2, M10. Summation of M alpha, alpha from 1 to 10, delta function x minus A alpha. Okay, just this is an example. Yes, I wrote. Example of presentation. Density can be represented as density of the string itself plus masses, sum of the masses multiplied by delta functions x minus a sub alpha. No, a alpha, a1, a2, etc., a sub alpha, and alpha goes from 1 to 10. Or if you want, I can write down string plus m1 delta function x minus a1 plus m2 delta function x minus a2 plus m10 delta function x minus a10. Okay, this is a very nice form of writing because theory is developed for the distributed load, not for concentrated load. Okay, beam equation is written in terms of distributed load on the right-hand side, not in terms of the concentrated load. Okay, so then we continue. So we write down again W of xt equals, and I will use the same notations as before. K. So that is k from 1 to n, from 1 to infinity, and then we have W k of x, and then we will have some function phi k of t. So that is what we would like to write there. Now, wk equals sine k pi x over L. Okay, so let us substitute there, and I will get EI forced derivative. So this is first of all k from 1 to infinity. Then forced derivative, k pi over L in force power. Then phi k of t. Then we will have plus rho a. Summation k from 1 to infinity. Wk, sine k, oh, here I forgot. Sine k pi x over L. Sine k pi x over L. Yes. Then phi k second derivative. This equals minus p0 sine omega t delta function x minus L over 2. Okay? Now we multiply by sine m pi x over L, where m is fixed. So I will get. And then we integrate between 0 to L dx. So I get EI k from 1 to infinity, k pi over L in force power, phi k, then integral from 0 to L, sine k pi x over L, sine m pi x over L dx, plus rho a, k from 1 to infinity, and phi k second derivative in time. And then integral sine k pi x over L, sine m pi x over L dx. Okay, this equals integral minus p sine omega t delta function x minus L2 sine m pi x over L dx. Now delta function, look, delta function x minus, let us consider right hand side, L over 2, sine m pi x over L, integral from 0 to L. Now this function is 0 everywhere except at L over 2. At L over 2 it takes very big value. Okay? That actually shows, okay, this gives me the value sine m pi over L, and x is this everywhere, this multiplication gives everywhere 0 except at this point where it gives me like this. Okay, I will explain you this. Write down this and I will explain you this further. So let us see, delta function x minus a, phi of x, f of x dx, say between minus infinity to plus infinity. This function is everywhere 0 except at a. Now, at point a, then, this function can be taken out at point a, f of a. Why? Because everywhere else it is multiplied by 0. This function is multiplied everywhere else by 0. Only at a, this function is not 0. So I can take this function at a outside. Then I will have integral from minus infinity to plus infinity, delta x minus a dx. This is 1. So delta function x minus a f of x dx equals f of a. So I can just write down one sentence before I finish. Delta function screens out, as it were, the value of a function. It takes from the, what is a function? Function is a one-to-one correspondence between argument, between values and independent variable. Here, delta function takes out of f only one value, and that is f of a. That is what product of delta function by the function does to the function. And we will continue discussion next time. And we have already the homework assignment.